Resonance is very important concept of this GOC. Not only GOC, it is the core, it is the heart of organic chemistry. So today we will discuss the resonance, right? First you have to understand that what is resonance. A resonance is the delocalization of pi electrons. A resonance is delocalization of pi electrons. I write here this simplest definition: delocalization of pi electrons. But you may find it difficult to digest. You may find it difficult to understand this statement. You have seen different kind of definition of their in chemical bonding also resonance topic is there, that is very limited. In there you have learned that resonance is the phenomena of representing the same molecule in the different electronic forms. Understand what I am telling you? This is resonance is the phenomena of expressing the same molecule in many other electronic forms. All those electronic forms represent the same molecule. All those different electronic forms means only the arrangement of electrons is different in only the arrangement of electrons is different over there. Understand here you know one very good example, and I would like to take your example for your better understanding. I just take one example of CO3 2 minus carbonate. Here there is double bond in between this carbon, that oxygen, there negative charge, here negative charge, but there is other way of writing that this double bond we can write here, and this oxygen and that oxygen will have the negative charge. This one is like this. Again, there is other way that this will be here, this will be there. It means here these two, this will be having double bond and these two will be having the negative charge. There double bond, here negative charge, and here negative charge. This kind of example on the name of resonance, and how it is resonance that you see that the same carbonate is represented, expressed in this form also, that form also, that form also. You can say, sir, all these forms are same, but understand these all are not same, because in this case this oxygen is having double bond, in this case this oxygen, and in third one that oxygen, means this pi bond keep on changing its place. Pi bond keeps on changing its place. This thing we are getting this thing we are getting from this one. So this is the point here. This way of expressing the same molecule is called resonance. Then you can ask me, sir, what is the point of this definition, delocalization of pi electrons? The delocalization of pi electrons is not different from this definition, where we say a resonance is the phenomena to express the same molecule in different electronic forms. It's not different. How it is not different? Let's understand here delocalization of pi electrons. First you have to understand here the pi electrons. What are if you answer like this is correct, but this is not 100% correct. It's a partial answer. It's not complete answer, right? What are the pi electrons that you understand? The pi electrons means electrons present in unhybridized orbitals. Electrons present in unhybridized orbitals. Okay. Pi electrons is that. Unhybridized, do you know? Hybridized and unhybridized. Here, how your definition will be justified? Electrons present in pi bonds. Yes. Which orbitals form pi bond? Do you remember? Recall this part. Recall this part. Which orbitals form pi bond? Only unhybridized orbitals form pi bonds. Hybridized orbitals always form sigma bonds. Unhybridized orbitals only undergo lateral overlapping, form their pi bond. Okay. So then your point is correct. But why I have written? Because you may have another situation where electrons are present in unhybridized orbitals but not forming pi bond. Understand? That time how you count pi electrons, that is very important one. This only example you take. Here 2 to 4 we take here. Here also we take. Now I am telling you, as per your concept, as per your perception, how many pi electrons are present in this one? 2. How many pi electrons are present? Only 2. Where is that? The pi bond is there. There, sir. But I will say here there are the 6 pi electrons. There are 6 pi electrons. Certainly here we have one sigma, one pi, one pair of electrons sigma, one pair of electrons in pi, so 2 electrons here. And the negative charge, what we say, which is capable to move, that is also present in the unhybridized orbital and pi electrons only. I am giving another good example. Okay, you will understand this one. When we write here the CH3, CH2, CH2 minus, we try to know the hybridization. Understand, listen this concept very carefully. When we write like this, CH3, CH2, CH2 minus, the negative charge here present, and what is the hybridization of this carbon atom? Its hybridization, you will say, sp3. 3 bond pairs, 1 Cc, 2 Ch, and 1 lone pair of electrons in the form of negative charge. So total 4 electron pairs, 3 bond pairs, 1 lone pair. Here we get negative, so its hybridization is sp3. Fine. Now I change here the situation. I write here CH2 double bond CH, and here the CH2 minus. Here we have CH2 minus. There we have CH2 minus. Here I say the hybridization is sp3. What is its hybridization? Its hybridization is not sp3. Its hybridization is sp2. Whatever rules you have learned to predict hybridization will not conceptual. It's conceptual. Here you have to understand that why its hybridization is sp2. Its hybridization is sp2 because there are only 3 hybridized orbitals. Which are those 3? One Cc and other Ch, other Ch. What about this electron pair negative charge? That is present in unhybridized pure p orbital. That is not participating in hybridization. Then you can ask, why it is not participating? It is not participating because it assumes greater stability when it moves. It interacts with this one. So as if this is sp3, then this cannot move. If it is sp2, then it can move. And if it is moving, then there it will be having greater stability. So it prefers to move here. Then you can ask another question, how it can move, sir? Because it can move because its hybridization is sp2 only. And there is one unhybridized pure p orbital, one unhybridized pure p orbital is there. That's why that orbital can entertain its movement, can interact with this one, can accept this pair of electrons, will form here one pi bond. There is possibility of formation of pi bond because one pi orbital is already present there. This can facilitate. Then you can ask me one question. Sir, if that is the case, then why because there is no scope of its movement. Why there is no scope of movement? Because this carbon is sp3. It has no any such unhybridized orbital to interact. Here all are sigma bond. There is no possibility, there no interaction, that's why it is not possible. But in this case, as the adjacent carbon atom, adjacent atom is available, for interaction, for the formation of another pi bond with one pi orbital, unhybridized orbital. That's why it prefers to change its hybridization and it is sp2. Sir, then is it possible in any other cases? It is possible in all such cases. Whenever you find the lone pair, whenever you find the negative charge present on an atom and on the adjacent atom, if the hybridization is sp2 or sp, then its hybridization will be sp2 only. Suppose I take this one and their adjacent one is sp2, so you just consider hybridization sp2, right? If adjacent one is having sp3, then this hybridization is optional for these atoms. I hope you got it. And I will be giving you more and more example. More and more example. Darun, that is also correct, as it can form double bond, what I am talking, that's why also you can say sp2. That is very nice interpretation, right? As it can form sp2, form pi bond, that's why also you can say. So that thing you have to understand where it can form double bond, right? Very nice. Exactly, I am giving another example. You take this example, it's very known example NH. What is the hybridization of this nitrogen? Ahmed, what is the hybridization of this nitrogen? Hybridization of this nitrogen is sp3. Here NH, NC, NC in one lone pair, so its hybridization is sp3. Correct? Now I am taking another example. Here no negative charge. What is the hybridization of this nitrogen? Pranav, concentrate now. Okay? Will be available later also. First you concentrate here. So understand this one. What's the hybridization of this one? Rachit, very good. Its hybridization is sp2. You know why? Because, very good, very good. Because this can move. And why it can move and can form here double bond. How it can? Because this will be here. This bond will break down and we can have this kind of structure where we will write like this and their negative charge and this will be like this. So there is a possibility of this kind, it is happening. And that's why we say, assuming this kind of phenomena, assuming this kind of possibility, we say its hybridization is perfectly sp2. Its hybridization is sp3. Very good. I feel you understood this one very well, right? So this is the way we identified pi electrons. If I ask one question, how many pi electrons it has? 0 pi electrons. Number of pi electrons, let's discuss your question. Number of pi electrons you have to answer. Here CH2 number of pi electrons here CH2 double bond, there the CH minus, CH2 minus, pi electrons here, NH, number of pi electrons here, number of pi electrons here, number of pi electrons here. This is the first one, second one, third one, fourth one, and fifth one. Number of pi electrons in these 5. In first case, how many pi electrons? Good. In the first one, pi electrons only here 2. This negative charge, this electron pair is no more considered pi electrons. Clear? Because adjacent one is sp3. There is no interaction, no pi bond formation. That's why this is sp3, this one sp2, this one sp2, this pi bond 2 electrons. That's it. Very good. Here the pi electrons. Second one pi electrons, how many? This one, there is negative charge, adjacent one is sp2. Two pi electrons, total pi electrons is equal to 4. Very good. Third case, how many pi electrons? Third, how many pi electrons? When you write answer, you should write 3. There the 2, 4. Like that you should write. Otherwise there I will be confused. For which one you are saying 3 or 4? Right? Yes. But third, your answer is wrong. Because in this case, again this lone pair is there and adjacent one is sp3. So this one is sp3 hybridized. This one is sp3 hybridized, this one sp3. Here we have the pi bond, so only 2. In third one, how many pi electrons? Only 2. Because the nitrogen containing pair of electron is present in hybridized orbital, not in unhybridized orbital, right? Fourth one, how many pi electrons? Fourth one, how many pi electrons? Very good. 4, 0. In this case, no pi electrons. In this case, how many pi electrons? Fifth one. Very good. Fifth one, 6. 2 to 4 to 6. Perfect. Nice. Good answer. So one thing we have learnt, pi electrons means electrons present in unhybridized orbitals. So now you can justify it very well that in this case, how many pi, in carbonate, how many pi electrons are there. So as this can form here, double bond, this can move, so this is also pi, this can move, that is also pi, this one is pi, total 6 pi electrons. Correct. Now I will discuss here the other part of this definition, that delocalization of pi electrons. You learned pi electrons. Nice, I am very happy. What do you mean by delocalization? Delocalization, when something is localized. Here localized, when I say, understand the meaning of the localization, that if something has one more identity, and that is the location. If location is also one of the identity of that one, that is fixed. Location keeps on changing. Location cannot be the part of identity, cannot be one of the identity, then that is called delocalized. There in the class itself, when you are sitting 3-4 students, and always if you are sitting on the first bench in the middle row, then your teacher is having one impression other than your name. Yes, one fellow in the middle row of the class on the first bench, you are just creating one more impression, one more identity, and you are localized. But at the same time, when some of the fellow in the class sitting one day on the front bench, other day other bench, third day third bench, fourth day other bench, keep on changing the place, then the teacher is not getting connected with him so well and so precisely. That fellow is delocalized. When that fellow is changing its place, means delocalized. Same thing here, the electrons are localized, electrons are delocalized. If the electrons keep on changing the place, we say delocalized, right? So, delocalization of pi electrons, but for that, for the delocalization, there should be some space, there should be some possibility or not. Here, there is negative charge. Is it delocalized? No, it is localized, because this cannot change its place. Here you see this electron pair will be localized or delocalized? Will be delocalized. At present, this electron pair is here, but can change its place, will form double bond and can come to this place. So that will be delocalized. But here localized, here delocalized, can keep on changing its place, right? So now you will be very clear with this definition, delocalization of pi electrons, and why we say resonance is the phenomena to express the various structures for the same, various electronic structures for the same molecule. Because in the resonance, again I come to this point, again and again I am telling you this one, and you focus on this one, that I am telling you they are the different electronic arrangement, localization, delocalization. I am not telling you here the different arrangement of atoms. Atoms are not changing their places. Atoms are not changing. I am not talking about the change in the arrangement of atoms. No. Change in arrangement of atoms leads to isomers. You are getting isomers. But change in arrangement of electrons leads to resonance, and resultant structures are called resonating structures. Resultant structures are called resonating structures. I hope you got it. So here, where you will get resonance? Is there any condition for the delocalization or not? So for that, here types of resonance I write. Resonance types, there the first one, delocalization of pi bonded electrons with pi bond in conjugation. Conjugation means the alternate arrangement of bond. Conjugation, one next, one after one. pi bonded electrons with pi bond in conjugation. CH2 double bond there, the CH in there, the CH double bond CH2. This one is, I say, delocalization here. This is a conjugated system. Double bond is there, pi bond is there, again leaving one, again pi bond. This is the conjugated system. Here pi bonded electrons undergo delocalization with the other pi bond. How we break this one? We write, you see, arrow is also very important. What is the meaning of this arrow? Meaning of this arrow is this pi bond breaks down. Meaning of this arrow is this pi bond breaks down. In pi bonded electrons, both electrons of this pi bond will be there now on this carbon atom only. In this one electron is contributed by this carbon, other electron is contributed by this carbon atom. So when both the electrons will come here, you will write here the resultant structure like CH2 double bond CH, and there the CH, and here the CH2 minus. Understand, I am going to discuss here even minute detail. I need your attention. I say that in this pi bond, two electrons are there, one of this carbon, another of this carbon atom, and pi bond breaks down and both electrons will be accumulating on this carbon atom. We write negative charge. Negative charge means how many electrons are there? Negative charge always represents here, unit negative charge means how many electrons? 2 electrons. How many extra electron? 1 extra electron. That's why unit negative charge. Because both are accumulating here, but one thing you understand, that only 1 extra electron of this carbon atom has been taken by this carbon atom. That's why we say unit negative charge. And as this carbon atom has lost one of its electron, so this will be having positive charge. It means this orbital is vacant. Earlier how the bond was there? This was the pi bond here. This pi bond was there like this. Electrons are here now. Now both electrons are here. Then the negative, this orbital is vacant. This orbital is vacant. Exactly. That's why we have it in the positive charge. This is ready now. Here positive, this is vacant now, there is negative charge. Now this is the vacant, so this can also accept electron and can form the pi bond. So what is happening here, this carbon is taking both the electrons and giving to this one, right? So when this carbon, again there the 2 electrons are there in this one, in this pi bond. 1 electron of this carbon, 1 electron of that one. So taking this electron, both the electrons, this one is taking both the electrons. So this carbon will be having 2 electrons. And with the both electrons, this orbital will be shared and will go there. We express this one like this. It is spreaded in between these two, and for that this orbital is taken, right? This carbon is left with no electron now, CH2 plus, because its orbital is vacant. This orbital will be shared now. So CH2 and there the CH double bond there, the CH and CH2 minus. You understand that how it forms, how electrons move. CH in there, the CH double bond CH2 we have written like this. Again this one like this. Electrons move, changing its place. In this case pi bond is here, now the pi bond is there. It is delocalized. Correct or not? This is called delocalization. Here delocalization is possible. Here this delocalization is possible because pi bonds are there in conjugation. This is the way you will break one pi bond. You will write there negative, you will write there the positive, and then the other bonds will follow that one. And this kind of thing is happening. Here, same thing you can write CH2 double bond there, the CH. Otherwise, you take the better example, more prevailing example, benzene you take. This is benzene. What happens in this case? Audio is there. You break it, we break it. What I should write? I take this one is 1, this one 2, this one 3, this one 4, this one 5 and 6. We break the bond in between the 1 and 2. Ajay, once check it. Ajay, any problem with the audio? So, in this case we break one pi bond. When we break here the pi bond in between 1 and 2, then what we write? We write negative charge on the first. Positive charge on the second one. Their negative charge let remaining as it is in their positive charge. What we'll do now? What we'll do now that there, this one is 1, this one 2, this one 3, this one 4, 5 and 6. What's the next one? We'll break now there the pi bond in between there the 3 and 4. There the 3 will be having negative and 4 will be having positive, and so this negative will shift in between 2 and 3. Why this shifting is possible? This shifting is possible because there the second place, one of the orbital is vacant. So what I mean to say, what is the resultant? Comes on this 4th place, 5th place, and the 6th place is there like this. Next you see what we will do. We will break here the 5 and 6, and that bond between the 5 and 6 will be moving towards the 4 because the 4th one is having the vacant orbital. So that is moving. And how to indicate that? You see, it must be indicated in the middle of the bond. When we show exactly on the same carbon atom. Just give some in the chat, you write some instruction, okay? You write there, refresh it or something, because he is just finding difficult. Is now there is bond, their negative charge, and now the positive charge comes to this 6th place. 6th place positive charge. This is the first one, and a first one negative charge in there, the 6th one positive charge. What next? Next is negative charge is there, positive charge is there. It means Here is the vacant orbital, there one of the orbital is present with the 2 electrons. So this can interact with this one, a new bond will form. This one, this one, this one. Correct. You see there this structure and this structure. This is also benzene and this is also the benzene. We say these structures as resonating structures. We say these structures canonical structures. Here you understand that you have written like this, you have written like this. In this case, there is double bond in between 1 and 2. In this case, there is single bond in between 1 and 2. What we say this one? Delocalization. It is not fixed at one place. It is changing in its place. The pi bond which was there in between 1 and 2 is now in between 2 and 3. Which was there in between 2 and 3, that is now in between 3 and 4. Changing its place. And keep on changing its place. There is the continuous delocalization because there is a scope, and how there is a scope, that is very clear in this case. These are the intermediate canonical structures. These are the resultant canonical structures. These are resonating structures. What we say? Resonating structures. We also say canonical structures. Okay. Means in the resonance, when you express one of the molecule in the various forms, in the various electronic arrangements, those various electronic arrangements are called resonating structures, canonical structures. I hope you got it. If there is no vacant orbitals, then there is no resonance. That only we explained now. In this case, you see no vacant orbital, no resonance. You cannot expect we have, this is one class of delocalization. I am going to discuss another class of delocalization. Delocalization of pi bonded electrons with pi bond in conjugation. This is one. Just you wait for the other class, other type basically. I am going to discuss here second one, delocalization of pi bonded electrons with unhybridized orbital. You know the meaning? Unhybridized orbital, what we say? We say pi orbital with no electrons. In this case also you can have delocalization. Delocalization of pi bonded electrons with unhybridized orbitals means pi orbitals with no electrons. You may have this kind of situation for the delocalization. One example you take CH2 double bond, there the CH and there the CH2 plus. What is the hybridization of CH2 plus? Hybridization of the CH2 plus is sp2. This one is sp2, its hybridization is sp2. When we say sp2, it means there is one unhybridized orbital here. And when we say plus, it means that is vacant. When we say plus, then that is vacant. So in this vacant orbital, here bonded pair of electrons can go. I have written this bonded, the movement of this pi bond in between these two atoms. It is not simply given to that positive. It is there in between these two. It means now there will be sharing in between this and that. In the resultant one, we write here the CH2 plus. Now, this carbon will be having one of the orbital with no electrons, because this carbon has taken those electrons from this one. So, this is left with one of the orbital with no electrons. So, CH2 plus and there the CH double bond CH2. Okay. Now you see, now again you can reverse. This can be very long one also. I am discussing here one more, right? Third one, you see there is a third one. How the video will be repeating, right now it's live. Maybe there when you are refreshing, there is some time lagging is there. So, you should not worry. You can refer, if you find it bit inconvenient, you can refer this lecture again, because this will be uploaded. In that time there will be continuous movement, right now. So, no need to worry. What is there? Please concentrate on this. Third one, delocalization of pi bonded electrons with pi orbital with 2 electrons. Understand? I am giving you all possible options. All possible options. You cannot have any example more than that, right? I am going to take here the 4, and the complete resonance of the organic chemistry will come under these 4 categories, right? So, this is third one, delocalization of pi bonded electrons with pi orbital with 2 electrons. Pi orbital already I told you, unhybridized orbital. So, CH2 double bond there, the CH2 minus. We discussed a lot. This will help you a lot. Its hybridization is sp2. Today only we discussed. So, this electron pair is there in, this is also pi electrons. Now, the pi electrons will be moving towards. How it can move towards? Yes, because this is also sp2. This has one of the unhybridized orbital. But then you will ask, why sir? That is already occupied. Not a problem. That is already occupied, that is already having bond with the other carbon atom, not a problem. If that is giving, then this carbon will advise that you take this pi electron pairs. Will like this. I am taking from this one, so you take mine. Will be pushed there, then there will be negative charge. So, this one is ready now to accept electrons. So, the resultant one is now CH2 minus CH double bond CH2. There is no pi electrons, no negative charge here, because that electron pair is now in the form of pi bond here in between these two. And what about this one? This was forming one pi bond with this one, given its own electron also to another carbon atom that you take, and so this one is having negative charge. This is also one of the way of delocalization. In this case, localization, we have to use the two arrows simultaneously. It is not like the positive where the single arrow is enough, two arrows, because we have to express that how there the next place is available for delocalization. I am just taking the bigger system of this one. I take the bigger system, CH2 double bond CH, in there the CH double bond CH, and here the CH2 minus. Bigger system. In this case, this electron pair is coming in between these two. I say this is 1, this one 2, this one 3, this one 4, this one 5. What will you write now? You will write here the C double bond CH without any change, and this will be having, as this is coming here, so pi bond will be there in between 1 and 2. But how is that possible in this present condition? Because then this carbon will be having 5 bonds. So this carbon is losing this one. So this third carbon will be having non-negative charge. So now this second carbon atom is ready to form pi bond with this first one. Yes, it is ready now. This third carbon atom is now again giving its electrons to this fourth one. How it will be giving? For that the fourth has to be ready. And how it will be ready? By giving its pair of electrons to the fifth one. Now you keep this one. I am taking from this one. So the resultant structure you will be getting here the CH2 minus, and now there double bond in between the fourth one and third one, and the second one and there the first one. This is the way delocalization is going on. Are you talking this problem? This third case or the second case? May try any. Which case? This third one or second one? Third one. Okay. Third one, negative charge is present here. Means this orbital is having 2 electrons. This orbital is having 2 electrons. So, and its hybridization is sp2. This is unhybridized orbital as we discussed earlier, because the adjacent one is sp2. So, with this electron pair, this carbon can form a new pi bond with this carbon only if this carbon will be losing its own pi bond with that carbon. So, it is happening. This carbon atom, this adjacent carbon atom is taking this electron pair with this carbon and losing this pi bond to that one. So, this another carbon is taking this pi bond and forming negative charge. Negative charge means bonded pair of electrons accumulate over there, that is why negative charge. In this one, 2 electrons are there and one is there of the same carbon atom, and 1 electron from this carbon it is taking. So, it is non-negative. This is the way it accepts. This is the way here the electrons move. Here also the same thing, this electron will be moving, pi bond will form, but for that it has to lose. So, very first we write negative charge here. We have written negative charge, there pi bond. Now, again this negative charge can go further, will form here the pi bond, then for that this will be moving there. So, you express all this. These are various electronic arrangements for the same molecule, right? These are called, as I said, resonating structures, canonical structures, right? So fourth one also you take, one more situation we have there, the delocalization of pi bonded electrons with pi orbital with one electron only. Yes. Is it possible with one electron? Yes, it is possible with one electron also. CH2 double bond, there the CH and there the CH2, this carbon is present with one electron. We say this space is free radical. What we say? Free radical. Free radical. What is its hybridization? sp2. Hybridization is sp2. What is the meaning of sp2? There is one unhybridized orbital which contains one unpaired electron. Okay. This is unhybridized, unpaired. So now in this case, as this is unpaired, so this can accommodate only one electron. Here there is no movement of two electrons. There is movement of only one electron. It cannot take two electrons. So here this adjacent carbon atom is coming with only one electron towards this one. Half arrow. Half-headed arrow. This is the movement of one electron. So this carbon, when going to this carbon atom with one electron, then what will happen there? This carbon is coming with one electron. This is having one electron. So one pi bond will form. Then what about this carbon? This carbon is left with its own electron, unpaired electron. So what is the resultant species? CH2. This electron is left. And what about this carbon? It has utilized its own carbon atom this side with this one. So now this electron pair is already here. This what has been taken, that is there. Okay, bond formed. And now we find that electron is there. Different electronic arrangements. This is 1, this one 2, this one 3. In this case we observe there is double bond in between 2 and 3. Now there is double bond in between 1 and 2. This is called delocalization. I am telling you, you cannot have any more example. You cannot have any more example. 4 categories only. Delocalization of pi bond with pi bond, delocalization of pi bond with carbocation, with one of the unhybridized orbital, pi orbital with no electrons. No electrons means carbocation we say. Delocalization of pi bonded electrons with one of the pi orbital with 2 electrons, carbanion, that is a negative charge, it is there. And delocalization of pi bonded electrons with pi orbital with 1 electrons, free radicals, 4 categories. Okay. So this is the point here, that let's take here the benzene, and I explained that this is one of the canonical structure of benzene. One of the canonical structure of the benzene, one of the resonating structure of the benzene. And what is the other one? This is moving here, that is moving there, and we write the another one. double bond here, double bond there, double bond. This is the another canonical structure of the benzene. A benzene is this or benzene is that. What is benzene? Because I said that the same molecule is expressed in the different form. So as that is the same molecule, then what is the meaning of are resonating structures, canonical structures, and also called contributing structures. Also called contributing structures. We also say contributing structures. This looks more meaningful. Contributing structures means for one molecule. When you write here the various arrangements of electrons, various resonating structures or canonical structures or contributing structures, it means these various arrangements contribute their own properties to the actual molecule. That's why we say contributing one. None of the arrangement is complete in itself. None. This is one of the contributing structures. So this is not complete in itself. This is another canonical structure. This is not complete in itself. Benzene is neither this nor that. Benzene is something different of this kind, which is having like that. When one molecule shows resonance, means many canonical structures what will be there, all those canonical structures are contributing structures and none is having individuality. Any of the canonical structure cannot be considered that molecule. All are incomplete. There we choose one of the structure to represent that molecule. This is a different thing. We write this one, we say this is a benzene. Okay, you say benzene, there is no much problem, but you should not understand this only is benzene. Benzene is something else. Then you will ask me, with this statement you are getting more and more confused. आप क्या बात कर रहे सर? Yes, what I say that as per this structure, let's mark these carbonatoms 1, 2, 3, 4, 5 and 6. 1, 2, 3, 4, 5 and 6. This structure suggests, you check this right now. Joined recently, who joined after the break, they will find their system by default in the mute. By default, that will be in mute. So what you should do, first you should check that one, you should unmute that one. Still if you are getting problem, you should refresh that one, you will be getting. Okay. I have here the two system. One where I can see the chat box and the videos, and other one where the live is going on. Okay. Fine. So What I want to tell you, when you say this is the benzene, don't misunderstand. In this structure, there is double bond in between the C1 and C2, and there is single bond in between C2 and C3. When the single bond is there, then the single bond character will be there. When double bond is there, double bond character will be there. But in the actual benzene, there is no single bond character, there is no double bond character. Then how it is benzene? You write this structure. It is one of the best canonical structure. It is so good looking benzene kind of structure. We understand this only is the benzene. Actually, this is not benzene. This represents benzene. Actual benzene will be something different. Actual benzene, honestly speaking, actual benzene cannot be written. But it represents actual benzene. It does not represent actual benzene. We write. This is not the correct representation of the benzene. This is also not. This is called canonical structure. That is called canonical structure, and this is called resonance hybrid. This is called actual structure, actual molecule which is having resonance is expressed by resonance hybrid only, and none of the canonical structure represent the entire molecule, the complete molecule. Canonical structures are contributing structures, contribute its properties to the actual molecule as per stability. The canonical structure which is more stable, that contributes more. The canonical structure which is less stable, that contributes less. Here I will tell you one what is canonical structure that I would like to tell you. Suppose I am taking class, physical class, you understand, not physical chemistry class, okay. So when I take your class, one of the parent is coming and just saying to me, ki sir, you are simply sitting in the chair and keep on dictating the things and you are not taking care of all the things. So I am very upset and I have to give some evidence that no, I am not doing like this. So what I do, I bring one camera and I am giving one fellow and say that okay, you do one thing, that you take some random pictures. So he is taking some of the pictures when I am taking the class. In one photograph, I am there with just beside one fellow, in another one just beside another fellow, third one, fourth one, fifth one, sixth one, seventh one, eighth one, location with the different students. Okay. And what do you think? When I am here and when I am in the class, that time what you observe, that I keep on moving in the class. So do you think that I am localized or delocalized? When I keep on changing the place in the class, I am delocalized. That is true. So I have taken all those photographs and I have given in front of the parent. I have shown him, sir, just to see these photographs. This is the evidence how I am taking care of the children. He is observing there the one photograph. Hey, lazy fellow, you are just standing. You are saying that you are moving. You are standing just beside one fellow. Then he will see other photograph. He will see I am still standing. But he is observing one thing, that I am standing but with somebody else. Again he see the third one. Again I am standing but with the other fellow. Fourth one also I am standing only but with the other fellow. Fifth one also I am standing but with another fellow. So in all the photographs I am standing only but with other fellows. Now you see, if he will see one photograph, what impression he will get, and if he will see the 10 photographs, he will think that I am lazy fellow, I am standing beside one fellow and I am carrying only that fellow. But when he will see the 10 photographs, he will have impression that no, I keep on moving in the class. I keep on carrying some other fellows also. I am attending their dots, I am attending their notebook and all those things. I am moving in the class, I am delocalized in the class. Understand this one, with the 10 photographs, with the 2 photographs, with the 3 photographs, he will be having one impression of my delocalization. If you will see one photograph, he will be damn sure that I am localized, I am not delocalized. But with the more and more photographs, with the 2 photographs, he will have some idea I am delocalized. But as he will see more and more photographs, he will be having more and more confidence of my delocalization. This only is the canonical structure. What is the canonical structure? Canonical structure is that one photograph. See again there the electrons are localized. When the third one, fourth one, electrons are localized. But what final impression you are getting? What final impression you are getting? Final impression you are getting that I am delocalized. DKJHA is delocalized in the class. Here it shows localized. This is localized, but the impression is delocalized because in this case double bond is here, in this case double bond is there. So I hope you understand here very well, you got it very well, that what is the meaning of canonical structure. DKJHA is cannot be described with one photograph. The DKJHA as a teacher will be described with many of the photographs. That is the real personality. Benzene will be described as the sum of those photographs, sum of those canonical structures, sum of these 2 canonical structures, and that is the resonance hybrid. That is now. Here also you observe that I keep on moving in this one. This one it is very clear. So this video one is resonance hybrid and still photographs are canonical structures. So understand, and this understanding will help you to understand there the resonance very well, right? You got contributing structures, resonating structures and resonance hybrid. Now we will discuss here rules for writing canonical structures. Canonical structures. Rules for writing canonical structures. Here it's not like that we can write in any of the manner. So understand first, here note down canonical structures are different arrangement of electrons, not atoms. First, this point should be very clear. Canonical structures are different arrangement of electrons, not atoms. Different arrangement of electrons are called resonating structures. A different arrangement of atoms are called isomers. Right? So first point is this one. Second one, every canonical structure is bona fide Lewis structure. Bona fide Lewis structure. Check it there. Very good. Bona fide Lewis structure. Bona fide Lewis structure means all the rules what you follow to write Lewis dot structure must be followed properly to write canonical structures. Right? So this is very important one. And what rule you mainly follow? You follow there all second period atoms should follow octet rule. You know octet rule is important, but this octet rule is limited to only second period atoms, not third period. Right? Here why I am telling you, whenever we write the structure, it should be followed strictly. I write here the CH2, there the minus CH double bond CH NNR2. We have one molecule of this kind. If we take here NR3, then this will be NR3 plus. Is it correct or not? If the nitrogen will be having the 4 bonds, then that will be having positive charge, that you know, because on the cost of that lone pair what is present on the nitrogen, new bond forms. So as it has no more that lone pair, that's why we put there the positive charge. One thing you understand, if there is CH2 minus and there the CH2 plus, there minus, there plus, what do you write? You write here CH2 double bond CH2, you write. These two are canonical structures. You can write like this. I want for that one. Okay? So again what I do, I take this example, it moves, this will be accumulating here as I explained yesterday. So I write here the next structure CH2 double bond CH minus now NNR3 plus. Okay. Now you see their NR3 plus, their negative, their positive. So what else we can write further? CH2 double bond CH, in there the CH double bond N R in R. Can we write like this or not? When there is negative, here is positive, so for this negative and positive, minus charge and there the plus charge, can we write this pi bond as it happened here? So is it possible? Not a valid canonical structure. This is not a valid canonical structure. Why this is not a valid canonical structure? Why this is not a valid canonical structure? This is not a valid canonical structure because in this case, this nitrogen violates the rule of octet. You see this one, 2 to 4 to 6 to 8 to 10. This nitrogen, which is the second paired atom, has now 10 electrons. It violates the rule of octet. There if you see minus and plus you have written, it is not violating the rule of octet, but in this case it violates. This is valid canonical structure, this is valid canonical structure, but this is not a valid canonical structure. You cannot write. So understand this one. That's why we say all second pair atoms should follow octet rule. Take contrary to this one. I take another example, same example. Double bond CH and P plus R and there the R. PR3 plus. Instead of nitrogen, I take here the phosphorus. And then it moves. This one is coming here. We write here one of the other canonical structure CH2 double bond CH. And here the CH minus PR3 plus. Okay. Now for this minus and plus, let's write one pi bond. I write here CH2 double bond CH and the CH double bond P R and there the R. We have done like this. Is it valid canonical structure? Is it possible in writing? Yes, it is possible. Why it is possible? Here also the same thing, this phosphorus is having now 10 electrons. Yes, nitrogen cannot have 10 electrons in the valence shell, but the phosphorus can have. Here you see 2 to 4 to 6 to 8 to 10 this phosphorus has. Because the third period atoms can extend its covalency by utilizing there the vacant d orbital. You know it very well, and that's the reason NCl3 forms, but NCl form, PCl5 forms. So that thing you have to take care, you have to understand, right? Here all second paired atoms should follow octet rule, right? Next one, this is the another point for delocalization. All atoms must lie in the same plane. In the same plane. For delocalization, this is very important point. For delocalization, this is very important point. What is the important point here? All concerned atoms must lie in the same plane. What is the meaning of this same plane? What is the meaning of this same plane? Meaning is, here physical plane, the atom should lie in the plane, and those orbitals which are interacting should also be almost of the same size, should be close. This is, you understand this one as I explained you earlier, otherwise today you see this is the benzene. This is benzene. Here we have NH2. This one is sp2, 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 sp2. All this is the planar molecule. This is the planar one. Now nitrogen is there. This has the electron pair. Even this one is in the same plane. Although, if I will write here the cyclohexyl group, then there this nitrogen will be having sp3 hybridization. But as we discussed yesterday, so now you know this nitrogen containing pair of electron can participate in this delocalization, can interact with the pi bond here. So its hybridization is sp2, same plane. Same plane, all atoms which are there conjugated should be there, sp2 or sp3 not possible, sp3 not possible. So you know this one is moving here and this is coming here, this kind of delocalization is possible. Now what I do now, you see, I write here N in one big alkyl group place here, big alkyl group place here, this electron pair is there. Still this electron is coming inside. Now I place here one alkyl group, here one alkyl group. Understand this one, when I place this alkyl group, this is much bigger. This Nr2 is also much bigger. Up there is height. Space is not enough to accommodate all these three groups in the same plane. There you understand, this is Nr2, this is methyl group, this is R group, this is R group, this is Nr2, this is Nr2, this alkyl group, that alkyl group. Up now this one is much bigger, this one is much bigger, so there is repulsion between these three groups. It's very difficult for these groups to be in the same plane because of this kind of repulsion. Then in order to avoid this repulsion, this Nr2 will go down. Up now there the repulsion will be reduced. This molecule will be stable. Otherwise, to avoid the repulsion, these two will go down, this will go up. Then also the repulsion is avoided. I mean to say, in order to avoid this repulsion, to impart stability, either Nr2 group will go downward or will go upward. These R groups will go downward or these R groups will be upward. The best is these two groups will go upward, that time Nr2 will go downward simultaneously. This is the maximum distance, greater stability. Otherwise these two will go down and this is the way these are arranged. And once Nr2 group will go down or up, then this nitrogen and this carbon both are no more in the same plane. I hope you understood. Pakka na? Either this Nr2 will go downward or upward, right? Now no more in the same plane. These two are not in the same plane. These two are not in the same plane, then that pair of electron cannot come into the ring, cannot interact with this pi bond, cannot interact. And this is called steric inhibition of resonance. Is inhibited. Resonance is prohibited. Delocalization is restricted. Its intensity is reduced due to steric factor. Due to steric factor because of non-planarity. In this phenomena is called SIR, steric inhibition of resonance. This is very important phenomena. It is affecting the properties of many of the compounds. Okay? I hope you got it. So this is one of the plane. Second thing, CH2 double bond, there the CH, and here I write NH2. Can you express here the delocalization? Yes, you can express. You can express the nitrogen containing pair of electron will be initiating here. This one is moving towards this one. Why it is moving towards this one? Because adjacent one is the sp2. There double bond, pi bond can form, but how it can form? It can form only if this carbon is just leaving this pi bond, leaving this pi bond. This carbon will take this pi bonded electrons, and then you write CH2 minus CH double NH2. Correct. What is wrong in this? One thing is wrong, that second pattern should follow octet rule. If you do like this, then the nitrogen is supposed to have 10 electrons. Supposed to have 10 electrons. When the nitrogen is having this pi bond, we don't know how it formed. We think nitrogen is having the electron pair, that is still there. And there the one electron pair, two electrons, 2 to 4 to 6 to 8 to 10, two NH bonds and two CN bonds, 4 bonds and one electron pair. Then you will see that, sir, what you are talking? Why 4 bonds? Then why there that lone pair? You have given that lone pair only. Ray, I have given lone pair. How you will know? It should be visible. It should be countable. So what you need to do, you have to write there positive charge to understand that this electron pair has already been given. If you don't write positive charge, then that pair of electron will be counted. If you write the positive charge, that positive charge indicates that that's why when the neutral atom is giving its electron pair, then that atom will have positive charge to count, to get, to manage this 8 electrons. So this must be given positive charge. One more thing I would like to tell you. Positive charge is very complicating. Positive charge is very confusing, because positive charge means we understand, you understand the vacancy. There the vacant orbital, deficiency, true. That is the general meaning of positive charge. But in this case, when the nitrogen is having positive charge, do you think this nitrogen is electron deficient? Do you think this nitrogen has different meaning. Yes, this thing you have to identify, you have to understand. This positive charge is different. This positive charge doesn't mean any vacant orbital, doesn't mean there the deficiency. It reflects, it indicates that it has given its electron pair to some other atom. That's why there we write positive charge. Are you getting this point? Understand and use in this way. Correct. So now it's very clear. Where is this electron pair? Where is this lone pair? This lone pair is present in the 2p. This electron present in 2p. Understand? I hope you know the electronic configuration of the nitrogen. That lone pair is present in the second p orbital. And which orbital is forming here? The pi bond sp2. So the second orbit p subshell or one of the p orbital is vacant. Two p only. So when a new pi bond forms, that new pi bond forms in between which orbital? Here 2p and 2 forms. This pi bond forms in between the nitrogen and carbon. Pi bond forms in between nitrogen and carbon. In between 2p and 2p. So we say 2p pi, 2p pi. A pi bond forms in between 2p and 2p. In chemistry, there is no, in this mechanism, there is no scope of coordinate covalent bond, right? Wherever we have coordinate, not the appropriate structure. Appropriate structure, when this oxygen is giving its electron pair to this one, then it should be written O plus, and as it accepts electron pair, it should be written minus. This is the right way to express. Got it? In Rachit, we are discussing resonance. Here, how you got the idea of the Lewis base? Rachit ji, you are getting the idea of Lewis base. What I feel that you are not perfectly present and connected with this one, because when I am teaching, I don't let you to think beyond my topic, but you keep on thinking something else. Here I didn't discuss ever about the Lewis base, and for the timing, I don't know what is the Lewis base. It is not the matter of one question. This is the matter of approach. That's why I want to address not only Rachit, other students also, that at present Organic chemistry, you stop reading from any other source, because once you will get the incorrect approach of reading organic chemistry, you will never learn organic chemistry. You will never learn. The reason is organic chemistry is very systematic science. It is entirely different from the physics, mathematics. It is part of chemistry. It has its own language. It has its own concept. Unless you understand all the basics from the scratch, you cannot develop the concept in the organic chemistry. If you will take some of the facts from this book, that book, then what problem you may have in the coming days, you have to depend on the mugging of all the reactions. You have to mug up. In that time, without any reason, you have to mug up. Mugging is required here also, even though if I will explain, but with logic you will mug up. Other way you have. So, what I request you all to be present. If I am teaching this one, you ask me question related to this. I don't want any overlapping of subject. My concept, my approach should not overlap. I will ask only that question, what you know, what I discussed. If anything else, the first I will explain that one, then I will use that one. So you understand, you have to go with me. If you have any problem here, you can ask me, as Satyavrat asked last part of this one. Here I explained steric inhibition of resonance, and that only I am discussing again. So you understand here what I am discussing? I am discussing here that how the pi bond forms, how the electrons move. I am explaining even this fact that how this one electron is going from this place to that place. What is the meaning of negative charge? What is the meaning of positive charge? Who cares all these small things? No one cares. And most of the people don't understand the subject because of these small things. I am explaining these small things also. What is the meaning of positive charge? I explained this one, the negative charge means one extra electron, but two electrons will be there. These are very small things, but that only make the concept. So what I would like to say, there nitrogen contains this pair of electron in the 2p, and this carbon is also having the electron in the 2p. There the 2p is forming bond with 2p. So now when this electron is moving here, so the 2p orbital of nitrogen is interacting with the 2p orbital of the carbon, and we are getting here a new pi bond, and we say 2p pi, 2p pi, because it is a pi bond. Understand this. Here now I write CH2 double bond, there the CHF. Similar resonance you will observe. Similar resonance. Fluorine contains here the electron pair, and that is moving here, and so it moves here. What kind of interaction is here in between the F and carbon? What kind of interaction? Where is the electron pair in the F? In the F, where is the electron pair? 2p only. Which orbital is here available for interaction? 2p only. So what kind of interaction is there? Again 2p and 2p. So we say 2p pi, 2p pi. Okay. Now I write here the CH2 double bond, there the CHCl. I want to listen from you now. What kind of not move? You have to write. Give me one response. What kind of interaction, what kind of pi bond forms here in between the Cl and carbon? Cl and carbon. Exactly. It is 3p 2p. This one is the 3p pi and 2p pi. Fine, very good. When we take here CH2 double bond, there the CH and there the Br, there also electron. What kind of interaction is there in this case? Br to CH, Br to CH, Br is 4p pi 2p pi. Okay. And what about this one? CH2 double bond, there the CH and there the iodine, this electron pair. What kind of interaction is there? What kind of interaction? This one is moving here, this is going there, so this one is 5p pi and there the 2p pi. Understand? I hope you got it. Very good. See, we are getting here the different kind of resonance is there from the 2p to 2p, 3p to 2p, 4p to 2p, 5p to 2p. This is the resonance, and that resonance cause here the pi bond formation. So we get here the pi bond and there the 5p pi 2p pi. You know, here for the pi bond formation overlapping is there, lateral overlapping. And which one is overlapping? Here, what is the difference in the 2p and 3p? 1s and 2s. 1s is this much, 2s is this much, 3s is this much. S is spherical only, P is dumbbell only, D is double dumbbell only. Then what kind of difference in there in the 2p, 3p, 4p, 5p? There is difference of size. Now you see, when I say there the 2p to 2p, it means this one 2p, this one 2p, almost same size. Good interaction. But when we say 2p and 3p, then what happens here? Then their interaction will be there in between these two. When we say there the 2p and there that 5p, socho, what kind of interaction will be there? What kind of interaction will be there? Is it effective? Do you believe in this kind of interaction overlapping? In the resonance, for the delocalization, interaction of orbitals is required. And what kind of poor interaction will be there in the 2p and 5p, 2p and 4p, 2p and 3p? Where it is the most effective? It is most effective in the case of 2p and 2p. After that, somehow the best in 2p, 2p. It is possible in the 2p and 3p also, but not as good as 2p and 2p. It is possible in the 4p, 2p also, but certainly not so good. So the point is here, the effectivity of this kind of delocalization, for us it's not difficult. Okay, let us write this one, it is happening, it's over. No, it is not over. We have to see inside what is going on, whether it is effective or not. Because not only we have to see the arrow, we have to see the impact of this arrow, impact of this pi bond formation. Because our responsibility is to understand properties and to predict properties. When we know this kind of poor bond formation will be there, then certainly this interaction is very poor. So, what is the same thing again you say that 2p and 3p both are not in the same level. 2p and 4p not same level, 2p, 5p not same level. So, this thing also you keep in this category for delocalization. All atoms must lie in the same plane, and if there the planarity is getting affected, then there the extent of resonance is also affected. The quality of resonance will be less, quality of delocalization will be less. Yes. So, I hope you got the significance of this statement, right? Just give me 5 minutes. These things are required. After that, okay, all canonical structures should have same number of electron canonical structures should have same number of electron pairs. Number of electron pairs should not be changed. One thing is very clear, sigma bond will not be changed, sigma bond electron pair will not be changed, certainly, because there is no different arrangement of atoms. Basic structure will not be changed. Then what is the meaning of here the electron pairs? Pi electron pairs. So, pi, we write here CH2 double bond, there the CH, and there the CH double bond CH2. How many electron pairs we have? There the 4 electron pairs, 4 electrons, 2 there, 2 there, 4 electrons, and there the 2 electron pairs, 2 electron pairs, pi electron pairs. We do this one, we break here, we write like this, we have written CH2 plus CH double bond CH, and there the CH2 minus. How many pi electron pairs? There 1, and this negative charge is also, so in this case also 2. These two are these two are canonical structures containing the same electron pairs, pi electron pairs. I write here now one more way, CH2 dot. We take 1 electron from here, 1 electron from here, and we write here the CH double bond CH, and there the CH2 dot. You see this one. I write like this, half arrow, 1 electron is left here, 1 electron is left here, and resultant structure is this one. Nothing wrong. This is also one of the different electronic arrangement. Yes, NP pi, where n belongs to period, correct. So, this thing you understand. In this case, how many pi electron pairs we have? Here 1. What about this electron, that electron? 1 here, 1 there, so 1 plus 1, 2 divided by 2, there the one more electron pair, huh? No, it is not your mathematics. This one is unpaired electron, that is unpaired electron. We don't consider here electron pairs. In this case, we have only one electronic arrangement. This is also one of the different electronic arrangement for this 1,3-butadiene, but this is not the canonical structure because it is not following this basic rule. All canonical structures should have same number of electron pairs. That is not happening here, it has only one, so this is not a valid canonical structure. Understand this one. Already I explained, Abhinay, that positive charge really represents the vacancy of one electron, right? But sometimes it does not represent. I explained there this condition. It does not represent the vacancy of one electron. I explained it very well. It does not represent the vacancy also. It has given its electron pair, that's why it cannot accept one electron. This nitrogen is not having capability to accept one electron. It cannot. So don't understand that way. I have given there the two meanings of the positive charge that you understand. Okay. When any of the atom is losing one electron, then there is the positive charge. Unit positive charge. 2 electrons, dipositive. All canonical structures should have same number of electron pairs. Yes, these are the rules. These are, you can say, as the nature of canonical structures, right? Now, next we will discuss that which canonical structure is more stable, less stable, their rules to predict the stability of various canonical structure, right? So now we will take there that other part of canonical structures, stability part. Stability part means here we have to discuss, as I said, that canonical structures contribute their properties as per their stability. So here one thing understand, the charge separation increases energy. Charge separation increases energy. Charge separation increases energy. What is the meaning of this? I take here CH2 double bond CH in CH double bond CH2. We break it. We write here the CH2 double bond CH plus CH2 minus. Here this negative charge and positive charge both are on the adjacent place in this canonical structure. You write another canonical structure now, and this positive charge is moving away from this negative charge. Understand? CH2 minus. This is 1, this one 2. So now we have to understand that which canonical structure is more stable, first canonical structure or the second canonical structure. Error on screen. Okay. No issues. Okay. So 1 or 2, which one is more stable? It's very simple one, that in this case charges, opposite charges present on the adjacent place nearby, that is more stable one. But here the charge separation is more, so that is less stable one. So you see stability, if we need to compare, this thing you keep in your mind. Okay. Next one, in order to write canonical structure when you break the bond, or in the various canonical structure when the charge appears, in that condition you understand the negative charge is more stable on more electronegative atom, while positive charge is more stable on less electronegative atom. Negative charge is best possessed by more electronegative, that is best held by more electronegative, so that is more stable one. What is the impact of this? Let's write here one molecule CH2 minus CHO. We write other canonical structure when this negative charge moves like this. This will go up. We write here CH2 double bond CHO minus. These two are canonical structures. Canonical structures are expressed with this double-headed arrow. Okay. So अब now again the point is 1 and 2. Which one is more stable? Which one is more stable? On more electronegative atom. So in this case this negative charge is present on carbon, and in this case that negative charge is present on oxygen. So which one is more stable one? Stability, when we compare, 2 is more stable than the 1. Okay. Right. Like that, here the next you understand the canonical structure having maximum number of covalent bonds is the most stable one. Right? The canonical structure having maximum number of covalent bond is the most stable one. We are considering the stability and understand this one. These are the few factors which will guide us for the stability. So when you write various canonical structures, just to take this only example here, I have not considered this, but this is also one of the canonical structure. So this is 1, this one 2, this one 3. Out of these 3, otherwise you take 1, 2 and this one you take here the 3. Out of these 3, which one is the most stable canonical form? In this case, the most stable canonical form is this third one. Why? Because in this case, number of sigma bonds in any of the canonical structure will not be different. Here pi bonds will be different. In the pi bond is there the one pi bond, here the 2 pi bonds. Please don't be confused. I am not counting here pi electrons. I am counting here pi bonds because I have written that canonical structure is more stable which is having the maximum number of covalent bonds. The covalent bonds, sigma bonds are same, pi bonds. We need to count here the 2 pi bonds we have, in this case 1, in this case 1. That's why this canonical structure is the most stable canonical structure. Okay? And that is why in general this molecule is expressed by this kind of structure. There, as I said, none of the canonical structure truly represents the actual molecule, but it's the fashion that we express that molecule with the help of the most stable canonical form. Right? One of the canonical form which is the most stable one, and that's why buta 1,3-diene is expressed like this. Right? Here, this rule, what I said, this rule is very powerful rule. It dominates over all other rules of stability that you understand. It dominates over all the rules what we have learned for the stability. Right? One more thing is there, that like charges on the adjacent places increase energy means decrease stability. Right? Like charges on the adjacent places increase energy, decrease stability. Right? What is the meaning of like charges here? Like charges, when we say positive charge and positive charge. Positive charge and highly electron deficient atom negative charge, or negative charge with the atom with the lone pair, because that would have also the same impact right now. Negative charge is the electron that has the electron pair, and the lone pair is also with that. So H double bond CH OCH3, this negative charge is here. ये तो बहुत बड़ा लिख रहे हैं. Okay, I'm writing bigger. CH2 minus CH double bond CHOCH3. Oxygen is there, it is the electron pair. If you take the other canonical structure, this will move here and that comes over this carbon atom, as you know. You write now the next one, CH2 double bond CH CH minus and OCH3. Now you understand, oxygen already contains pair of electrons. This negative charge is coming over that carbon atom which is just next to that. Here we consider the like charges on the adjacent places. The interaction of this negative charge with that lone pair is like charges, like negative charges, and that is extremely destabilizing, very unfavorable, and that's why this is extremely unstable, Like that, when you take here CH2, there the plus and there the CH double bond CH and CH double bond O. You understand yes, here you know, in such cases sometimes we don't compare also. Your point is correct. In these cases sometimes we don't compare also. Unstable, then that won't be considered valid canonical structure. This is also one of the structures must have almost same energy, so not differ much in their energy, right? And the canonical structure which differs with significant amount of energy, that is considered invalid form, right? No? So you understand this, your point is correct, like charge on the adjacent places, so this is more stable than that, perfect. CHO you write, and in the CHO kind of bonding, the oxygen is more electronegative, there is pi bond, so the bond breaks down and the negative charge is almost all the time on the oxygen, and the carbon is significantly electron deficient. Carbon is significantly electron deficient, partial negative, partial positive. This is not simply partial negative, simply partial positive. Significantly partial negative, significantly partial positive. But we don't have any other term to express here that significant amount of deficiency. We know only two terms there, the partial, this delta positive, and there the complete positive. There is nothing in between to express, but you understand. So when this positive charge attracts electrons, You will write here one of the canonical structure CH2 double bond, there the CH, in there the CH plus, in there the CHO. This CHO, this CH carbon is already significantly electron deficient and the positive charge arises just adjacent to that. Understand? This is again the case of like charges, like positive charges on the adjacent places, and that's why this is far more stable and this one is extremely unstable, and it is not advised to write. We are not advised to write this kind of canonical structure. Okay, fine. Here I have summarized those rules which affect the energy of canonical structures. You understand this one, and one thing I am telling you. Okay, learn how to use this one. I am giving one example here, and you predict their stability. Just two examples I will give. First example you take. Example 1, CH2 double bond, or you take here CH2 plus CH CH double bond CHF. I write its other canonical form. Fluorine contains pair of electrons that is moving towards this, that is moving there, and finally we write CH2 double bond CH double bond F. Is it right canonical structure? Is there any mistake in this? Yes, mistake is there. What is the mistake here? Mistake is fluorine, one of the neutral atom which contains this pair of electron, that has given its pair of electron in this resonance. So as it has given its pair of electrons, so certainly this will be having positive charge. But remember, I discussed yesterday, this positive charge doesn't mean deficiency. This positive charge doesn't mean the vacant orbital at all. Positive charge is there to manage octet. Positive charge is there to express that this fluorine has given its pair of electrons. So now I have written here the two canonical structures, 1 and 2. Compare their stability. That is still maintaining octet. That is correct. Here once we have given the positive charge, it means it is maintaining octet. It has now only 8 electrons in the valence shell. Okay. Fluorine can have double bond, right? There is no issue at all. Oxygen can have double bond, nitrogen can have double bond. Since the beginning of this, we have been writing right now the region for that we have written 2 to 4 to 6, 1, 7, 7 electrons. This has given its pair of electron. There the positive charge. So how many electrons are left? So now you count 2 to 4 to 6 to 8. Where is the violation of octet rule? There is no violation. Fluorine can form if you put their positive charge. Oxygen can also form double bond if we put positive charge on that one. I want region here that which one is more stable and why. Yes, you are saying that one is more stable than the two. Some of you are saying in second there is a violation of octet. There is no violation of octet. First point. Second point, in the second case, one more important rule is involved where you have not focused. I thought you will just you will catch that point, because just 2 minutes before only we discussed that point and you are ignoring. Here we discussed the negative charge is more stable on more electronegative atom, while positive charge is more stable on less electronegative atom. Okay. So when the positive charge is there, this positive charge we have written on the most electronegative atom. That is the concern here. That may be difficult to digest. This structure is correct, but here this positive charge is coming on the most electronegative atom. Still there one problem, that is correct now. Still there one point, then also this only is more stable. Positive charge is there on the more electronegative atom, then also this only is the most stable. Why? Because it contains more number of covalent bonds. I just pointed out this point. You should not ignore this one. Just to see this, what I said, this rule dominates over all other rules, that the canonical structure having maximum number of covalent bonds is the most stable one. Here you see, in this case 1 pi bond, in this case how many? 2 pi bonds. Context I am giving one more. CH2 double bond there, the CHF. Now again this fluorine containing pair of electron is moving, and we write CH2 minus in there, the CH double bond F in plus. This is 1, this one 2. Which one is more stable? Which one is more stable? First or second, which one is more stable? In this case also the positive charge is there on fluorine. Can we ignore this one? No, we cannot ignore. Correct. We cannot ignore. Why we cannot ignore? We cannot ignore because in this case unnecessary charges appears without increase in covalent bond. We have the same number of covalent bond and then positive charge on the fluorine more electronegative, negative charge on the carbon unnecessarily. So all these things are increasing energy, and here first one is more stable than second one. Very good, well done. Okay, let's take here the second example. N triple bond N plus CH2 double bond N minus CH2 plus N double bond N minus CH2 N. All these are CH2N2. called diazomethane. Okay. Now this is 1, this one 2, this one 3, this one 4. Can you tell me what is the relation between 3 and 4? What are these two? 3 and 4, 2 and 4, 1 and 4. What kind of relationship is there? What are these two? What are these two? 3 and 4. Are these structures? These two are not canonical structures. Then what are these two? These two are isomers. Why not canonical structures? These two are not canonical structures because here atomic arrangement is changed. Canonical structures have the same arrangement of atoms. Atomic arrangement should not be changed. So, fine. Now, I exclude fourth one and I just want you to compare the stability of 1, 2 and 3. Compare stability of 1, 2 and 3. Correct. Not canonical structure. Atoms are arranged in different order. Rachit, very good. That's why atoms are arranged in different order. That's why these are isomers, these are not. Very nice. Which is the most stable one? 2. After that which one? 1. After that which one? 3. Why 2 is the most stable one? Why there the 3 is the least stable? First let us discuss this only. The 3 is the least stable one because it contains least number of covalent bond. In this case only one pi bond is there. In this case how many pi bonds? 2 pi bonds. In this case how many pi bonds? 2 pi bonds. So certainly these two are more stable than this. Now next here 2 and 1, which one is more stable one? Number of pi bonds are same. When the number of pi bonds are same, then we have to see some other things. Let us see here the charge. Nitrogen is having positive charge, nitrogen is having positive charge. In both the case, nitrogen is having positive charge, so this is also not the deciding factor. Then what next? This carbon is having negative charge, but there the nitrogen is having negative charge. So the point is here, nitrogen is having negative charge. Hold better this, that is more stable. Negative charge is more stable on the more electronegative atom. That's very nice, and that's why there the 2 is the most stable one. After that 1, after that 3. Very good answer. Very good answer. Very good. Very good. Okay, fine. Good. I just take here few seconds to clean this one. Right? I hope you have copied all these things. And I will come to the other part of this resonance. Just I will take 1 minute. Just a clean करने से. See, we have discussed there that rules for writing canonical structures, how canonical structures are written, but now I am just giving few examples. We will see the effect of substituents on the resonance. Effect of substituents on the resonance. We say this one resonance effect. We say this one meso. Here resonance effect. We also say this one mesomatic effect. Okay. What is this? This is the effect of substituents on the resonance, on the delocalization, the effect of substituents on the delocalization on the resonance. What effect? I take here one system CH2 double bond CH2. You take some bigger system also CH double bond CH2. In this case, we can take this bonded pair of electrons here, their negative charge, their positive charge. This bonded pair of electrons will move here, their positive charge. Okay. Now, nothing wrong if we take this bonded pair of electrons here, their negative charge, their positive charge. This will be moving here, their positive charge. You can show movement of electrons in any of the direction. No problem at all. Here, both the way electrons can move freely. There is no difference. Is there any difference? You can write like this also, you can write like that also. No problem at all. But if we put here, means you can write like this, or you can write like this and like that also. But if you put here one of the substrate like CH2 double bond there the CH and CH double bond there the CH and OCH3. Now one of the substrate like OCH3 is connected to this system. Now you see the impact. Can you write like this? Is it possible to write like this? Impossible. 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 Why? Here only we discussed the like charges on the adjacent places produce extremely unstable canonical structure. So if we do like this, negative charge will come over this carbon atom which is extremely destabilizing, unstable one. It won't happen. Their electron pair already we have, so this is the way. This way we cannot go, we cannot show delocalization this way. Restriction is there now. Okay? Now, then what way we can write? If the OCH3 kind of substance are present, then the electrons will be moving away from this one, not towards this one. Then you will be writing this one is moving here, this is going there, positive charge will be here. So this positive charge will be getting electrons from here. Yes, this is correct way. Yes, this will be happening. That will not be happening. It means what? It means if the OCH3 kind of substance is present, then this is controlling the direction of delocalization. This is putting lots of restrictions. This is putting its own impact on the resonance. Right? How? This time OCH3 is increasing electrons into the system. Here you will see it has given its own electron into the system for the resonance. It will be giving into the system. If this is the system, in this system, this OCH3 is giving its electrons and making this one more electron rich. Electrons are moving away from the oxygen, not towards oxygen. This kind of observation will be here. This is very significant thing. This will be affecting the properties of now you see. We have other kind of substance also. Here only in the same system CH2 double bond, there the CH in CH double bond CH, and we put here the CH double bond O. We are giving here CH double bond O. So, अब now again let's assume. Can you write like this way and this way? If you write like this, then there will be positive charge. And do you accept positive charge on this, on the adjacent to CHO? Not at all. You won't accept. Because this carbon is already highly electron deficient. So this won't accept positive charge on its adjacent place, and this won't permit this to happen like this. Electrons will not be moving away from this kind of substrate. Now electrons will be moving towards this kind of substance, right? So just reverse direction here now. So it would prefer to come like this. It would prefer to come like this, and then this will be accumulating, this bond will break down, this will be accumulating over oxygen, and this carbon will be accepting electrons from the system. Happening, this is very preferred because the negative charge will be coming over oxygen, and that is very much a stable one. So one thing you see that in this system, what you say, what is the role of CHO kind of substance? CHO kind of substance is making this system electron deficient. CHO kind of substance withdrawing electrons from the system. CHO kind of system forcing the movement, delocalization of electrons towards itself. So the nature you will find of these two substances entirely different. Earlier also, you know, we learned minus I groups plus I groups. Minus I when the electron is pulled towards the substance. Plus I when electron is given away from the substance, right? That is the internal current along the bond it is happening. But here it is different. It is upper layer. Through orbitals it is coming, it is going. There may be. Up now you see there the effect of the OCH3. OCH3 is the minus I group. If we are asked to indicate here the minus I direction of there the electronic displacement there along the bond, then still there the electrons are moving towards the oxygen only. That inductive effect direction is there towards oxygen, but resonance effect direction is there away from this one. There is the counter. One is pulling towards this one, that is the I effect, and the plus M effect or there the resonance effect is giving electrons away from this one. resonance is dominative. Resonance is very strong effect, much stronger effect than the eye effect. So here also now we have reached to one place understanding that these substances have to be classified there based on the resonance. What kind of effect it gives on the resonance, on the system, based on that, here we'll have O is called minus M minus R. All the substances are classified as plus mesomeric effect substance plus resonance effect substance minus mesomeric effect substance minus resonance effect substance, like that. So now very similar to inductive effect, we have also there is another classification of the substance based on this resonance effect, that is the plus M, or you can say plus R, or minus M or minus R. Here there I had given the order and you had learnt it. Here you can identify that which can act as the plus M and which can act as minus M. So I would like to ask you that which will be acting as plus M? Which will be acting as plus M when we have the OCH3? If you say the substance is OCH3, then the oxygen is free valent atom. It is the oxygen which is connected to the system. This is free valent one. So if in the substance the free valent atom contains minimum one electron pair, minimum one lone pair of electrons, certainly that will be acting as plus M. So this free valent atom must contain one lone pair in the form of negative charge or in the form of simple non-interacting lone pair, right? So it requires free valent atom must contain one lone pair. Then that will be acting as plus M. That is enough for the plus M. This is enough to identify. Again I am telling you, please don't misinterpret. I am telling you, in the substance free valent atom, it's not that anywhere of CH2O CH3 cannot be plus M, because CH2O CH3 the carbon is free valent, oxygen is not free valent. Okay, the plus M. What about the minus M? When we write here the CHO, this kind of substance, here free valent atom should have positive charge, direct positive charge. It's not like the nitrogen positive charge, or multiple bonds, means double bond or triple bond, multiple bonds with more electronegative atom. If that is with the more electronegative atom, then certainly that will be electron deficient, and with the help of more electronegative atom, that atom is capable to accommodate electron pair, capable to accept this pi bond will not go towards the less electronegative atom, and that won't be in condition to accept electron pair. So with the more electronegative atom, two things I have given: free valent atom should have positive charge Again, there is some limitation, restriction, positive charge not on the nitrogen and oxygen, or multiple bonds with more electronegative atom. This is very important for you. Multiple bond, double bond, or triple bond with the more electronegative atom. Why it works? Because if multiple bond is there with the more electronegative atom, then this one is electron deficient, and due to the cleavage of this pi bond, negative charge will come on more electronegative atom. This will be having the real positive charge. This is certainly in condition to accept electrons, to pull electrons from the system, and that's why that will be certainly acting as minus M. I hope you got it correct. Here plus M. Okay, I write the order. Okay, I write here the list of plus M, O minus, Nr2, NHR, NH2, OH, OR, SH, SR, NHCOR, OCOR, FCl, BRI. These are, understand and set in your mind. Okay, minus M, minus M, CO, Nr2, CO, OR, CO, OCOR, COX, CO, R, CO, H, C triple bond, N, S, O3H, NO2. OH also. This is in decreasing order. This is in decreasing order. Decreasing order means O minus is the strongest plus M, and here I consider the I is the least. You take this one is decreasing order. This one is almost, not perfectly, increasing order. Okay. One question Rachit has asked, there the CH2, otherwise you take here N double bond O, NO. What is NO? Anyway, you had to answer, this has electron pair. Nitrogen has electron pair. So certainly nitrogen will be giving. I said that free valent atom must contain one lone pair. Does it contain one electron pair, lone pair? Yes. Then essentially plus M. Essentially plus M. And at the same time, here the nitrogen contains double bond with the more electronegative atom also. So this one can act as minus M also. So NO is acting as plus M as well as minus M, both, but not at the same time. Depending on the situation, this NO can act as plus M also and minus M also. Here we have one more SOOR. Here also you see this sulfur contains pair of electrons. So how this will be acting? This will be acting as plus M because this has electron pair and this is acting as plus M. But again you see this has pi bond with the more electronegative oxygen. So this can act as minus M also. These are minus I group. The normal condition as minus M only, right? Minus I and minus M. But if we have the situation here like this, CH2 plus, CH double bond, CH and N double bond O, what is the role of NO here? In this case, NO will be giving its pair of electrons to this plus. This will be essentially acting as plus M only. And here you will be writing CH2 double bond CH and CH double bond positive charge. So here NO is acting plus M. Normal condition NO will be acting as minus M. In the normal condition, and there the SOOR will be acting as minus M. But when some of the strong electron withdrawing center is there in the system, that time SOR will be giving its pair of electrons. Not only this one, I will explain you that why this one is big, this one is stronger, why this one is poor, why this one is poor, why this one is poor, why this one is stronger, why this one poor. This kind of comparison also we will do, right? So here few points you have to understand, that I have written certain order. I have written here O minus, then there Nr2, NHR, NH2. You understand this one? O minus I have written as the strongest plus M. You know why? Because this is plus I as well as plus M. So both way electrons will be moving towards the system only. That's why this is the strongest one. O minus is the strongest plus I, and this is plus M also. The movement of electrons will be in the same direction. If you will take here the Nr2, this one is actually minus I, pulling electrons towards itself along that bond, sigma bond. But through pi bonds, we will be giving electrons. So there is fight. Internal current, internal displacement of electron along the sigma bond is there. Here this one is good plus M, strong plus M. But I have given here Nr2 is better than the OH. Why? Why Nr2 is better than the OH? Nr2 is better than the OH because this electron pair which is given to the system, that is present on the more electronegative atom. So this electron pair is more tightly held, so given less easily. Given, I am not saying not given, will be given, pakka given, but will not be given as good as it is given by nitrogen, which is relatively less electronegative. It matters. When it is more strongly held, then certainly the ease of its movement will be affected. That's the reason Nr2 is better than the OH. Next, here I am telling you, I have written here the two where whether you ask me or not, but I know when you will really learn, that time you will ask me. Today your attention may be a bit less, so you might not be relating facts, what I taught here, what I taught there. So these two things you have not related fast, but you will ask me that, sir, OH and there the OR, R is the plus I effect, and you say that this one is given. So then which will be the stronger plus M? Why OH? Why not the OR? There is a back support of the R plus I. So certainly this should be the stronger plus M. We expect, but it is not. Reason is, when we write the OH, OH is there always in equilibrium with the O minus. Wherever we have the OH, there the certain amount of O minus is certainly present. So when we see this one, suppose we have here there the OH, so you don't have only OH, we have there the O minus, the mixture of these two. So when we see the reaction here, then we see the reaction over this also, that also. There is some impact of O minus, and O minus is making this one very much effective. Then you can ask me, sir, if that is the case, then it should be happening with the Nr2 also. NH2 should be stronger than the Nr2. No, it is not observed. Why it is not observed? Because NH2 is not considered existing as NH minus NH plus as good as OH. This is not much more acidic. This is not readily ionized. Minus effect here we don't get, and it is observed. So you understand this point here that OH, OR, OH is more. Okay, fine, no issues. Then there the other comparison we have, that suppose there we have the OH and there the OCOR. This has the CO, so how this will be acting? This is having the carbon with the multiple bonds, so this will be acting as the minus M group. Is it correct? It's not correct. Why it is not correct? Because I didn't say that substituents should contain the atom with the more electronegative atom, multiple bond with the more, that I didn't say. I said the free valent atom if contains, here the free valent atom is oxygen, that contains electron pair. Yes. So this will be acting as plus M only. Then the point is OH and OCOR, which one is stronger? Certainly OH is stronger. Why OH is stronger? Because in this case this electron pair is 100% available to be given to the system only. But in this case this electron pair sometimes delocalized here, it has internal resonance system. So as its availability is less in comparison to this one. Why its availability is less? Because it is already delocalized. Where it is delocalized? With this COR. That's why you understand, because of its content delocalization, the availability of this electron pair is less. That's why this one is less in comparison to OH. Fine. You compare here OCOR and NHCOR. Compare these two now. Which one is stronger? Which one is stronger? OCOR or NHCOR? OHCOR or both are similar now. This is also plus M, this is also plus M. Why this is plus M? That is very clear, because the free valent atom is oxygen containing pair of electrons. Free valent atom is nitrogen containing pair of electrons. These are poorer than the NR2 and there the OH, because it has already one of the COR present. So it is already delocalized. So its availability is less, sometimes this side, sometimes that side. So fine, but when we compare these two, then again we have to come to the another point. Which is that point? That point is this is more electronegative, so that is better held. So out of these two, which one is the better plus M? Certainly this one is better plus M. Why this is better? Is present on the less electronegative atom. I hope you got it. Another comparison. Another comparison is, we have the F and there the Cl. Then the same concept will apply. Which is the better plus M group? Which is better plus M group? F or Cl? Which is better plus M, F or Cl? You will say that sir, Cl is the better plus M. Why? Sir, Cl is less electronegative. Cl is less electronegative. As N is less electronegative, and so better plus M, Cl is less electronegative, better plus M, but it is not correct. In this case, it is not. Already I explained this point, CH2 double bond there, the CH in there, the F in there, the CH2 double bond there, the CH in there, the Cl. Already I explained this point. I explained this point because I said that here the electron pair is present in the 2p and there the 2p. So the 2p to 2p, there we have the 2p pi delocalization. But in this case, we will be having electron pair is present on the 3p. So 2p pi and the 3p, 3p. P pi 2p pi or the 2p pi 3p pi, which is better? Ayush ji, which is better? 2p pi, 3p pi, or the 2p pi, 2p pi in the same range, that is better. So this one is better than this one, and so chlorine is better than the bromine. Bromine is better than the iodine, because in the bromine the situation is more worse. There is the 4p pi, 2p pi, 4p pi. Iodine is very worse, that is worst basically. There the plus m we have, but the condition is very poor. The reason you know, in that condition 2p pi, 5p pi. So fifth orbital p and there the second, both are least interacting. That is the point here, and that's why FClBri. Here we are considering their plus m impact based on that interaction. And which is the strongest one? F. Then there the Cl, then the Br, then the I. You don't think that it is here only. It is on other place also. OH and SH. Which is the better plus M? Which has the better plus M? OH or SH? OH or SH, which is better plus M? Avinay Rathore ji, how SH? Just now I explained. There the Cl or F, which is better? When F is better than the Cl, H will be giving electrons from there the 2p to 2p, but SH will be giving electrons from the 3p to 2p. Gandhi ji fellow. Already I have given this in order also, that OH is higher than there the SH, right? So understand this point. Here also the same thing, SH 3p to 2p, that's why it is poor. It affects a lot. Okay, come to the other point here. CO Nr2, CO, and there the H. I am talking here minus M. Minus M I am talking. Minus M, which has the better minus M? Their deficiency, their deficiency. If this deficiency is more, this will withdraw electrons more. Then this is better minus M. Greater the deficiency, greater the deficiency at C O, stronger the minus M. Stronger the minus M. That you understand? Greater the deficiency at C. Here it is hydrogen. There is deficiency, but it's the hydrogen which is interacting with this deficiency. But in this case, it is the Nr2 with its full plus M effect trying to reduce this deficiency. And this deficiency is decreased maximum by Nr2, which is the best plus M group, and that's why its withdrawing capacity, its minus M capacity is least. Okay. CHO is better. Suppose there be the CO and there the CH3. So this, even this CH3 is decreasing this deficiency. Either you take the plus I effect only, it is decreasing this deficiency. And when this deficiency is decreased, then its electron withdrawing capacity is also decreased. So in this case, we have only one concept, that greater the deficiency, higher the minus M effect. Greater the deficiency, higher the minus M effect. You see everywhere you will find the same thing. NO2 we have kept as very strong group. You know why? Because this N is connected with double bond O, and at the same time this N is having there the positive charge also, because it is written like this. This dative bond, as I explained you yesterday, yes. Yesterday I discussed this point, that dative bond is better expressed as the plus and minus, so this NO2 is better written like this, and this nitrogen is having positive charge, no doubt, and this multiple bond, so minus I effect is very strong, and their deficiency is also due to the double bond O is very strong. It will accept very effectively, and that's why this is considered as one of the strongest minus M group. Even SO3H is very strong one. Even Cn is very strong one, because triple bond is there, that carbon is very electronegative, and due to the multiple bond again that negative charge comes over the nitrogen. SO3H, because in that case two oxygen atoms, SO3H if you write, S double bond O, and there the OH, you see this one here, the two double bond O is there, that is trying to make this one more electron deficient, but the problem is there, it is sulfur, that's why. Otherwise it could have been the best, topmost. Remember, keep this point in your mind, and then see this order of minus M, everything you will find justified, right? Now, we have explained, we have discussed the basis of that order. Now, I am not giving you much scope to ask question later. Whatever question could be there, I have explained, I have raised. If some more questions you have, you can ask, I will discuss. But this order you have to fix in your mind now first. If you need to mug up, you mug up. You have to say immediately at least these groups. Other groups, you think and then apply your mind. You ask me, no problem. But these many groups should be there on your tongue now. This order you have to mug up now, right? Then only the next part of, that is the application part of all these things, will be very effective. Otherwise, in every example, you will ask me why OH is better, why there the NR2 is better, why O minus is better than that. If you will keep on asking me such silly things, such small things, what I already explained, then we cannot go forward. Do it, learn it. I am just winding it up, right? So, any question please? Any question? Anyone please? क्लास समझ में आ रहा है कि नहीं आ रहा जी? चलो आना चाहिए, सारा नोट्स कर लेना। Already I discussed now, Rachit, there the plus M effect of the same group OH already. Here we have discussed OH and SH. You see this one, that how OH is better than SH. In the same group FCl, BRI we have discussed. अब किसका लोगे? लिखोगे? Right. Thank you.